Hello and welcome to another lecture of Introduction to Astrophysical Fluids. I hope that you have been enjoying the course thoroughly. Okay, so as promised, in this week's lecture, we will be discussing the application of shock waves in astrophysics, and one application I already mentioned in the last lecture, that is the physics of the blast waves which appear during the explosion of the supernova. So supernova are extremely important objects to be studied in astrophysics. Okay, so I am not sure how many of you know what supernovae are, but here I am trying to give you a very brief introduction about supernova. So depending on the composition and origin, often the supernova, they are classified in several types. Okay, but two of them are of very specific interest. So in general, supernova means that, very roughly, a very high energetic explosion type of thing. Okay, explosion of a star. So that is the very rough meaning of supernova. Okay, now whenever in the framework of normal astrophysics we talk about supernovae, so we talk about supernova of type 1, and most frequently we talk about supernova type 1e. Now there is another supernova, supernova type 2, and that is also very usual. Usually we talk about supernova type 2b. Okay, now supernova 1, okay, is basically defined as the supernova which does not contain any hydrogen emission line in their spectrum. So that is the formal definition of supernova type 1. Now, there are 1A, 1B, 1C, okay, and of which 1A is very interesting, and this is caused by the explosion of a white dwarf. White dwarf is one of the very famous compact objects in astrophysics. Already we have mentioned about it while discussing the physics of accretion disks. Okay, so this supernova is caused by the explosion of white dwarf due to mass accretion from its neighbor star in a binary system. Now that neighbor star may be a less dense star, as we discussed in the case of an accretion disk, or a comparative white dwarf type of another compact object. That is also possible. Okay, so then after accreting a sufficient amount of mass, it actually the the compact object or the white dwarf, okay, explodes. Okay, and that causes supernova. Why that explodes, that's another story, and that for that I want you to search actually through internet, okay, or in various books, that to go into the detail. So this is, the current course is beyond the scope of discussing all those details. Okay, another thing is supernova type 2, and so this means that this type of supernova contains hydrogen emission line in the spectra. Okay, now this is, whenever we are talking about type 2, usually we talk about type 2b, and this is caused by the sudden and rapid collapse and a violent explosion of a very massive star of mass ranging from 8 solar mass to 40 solar mass. Okay, so this needs a mass accretion from a binary neighbor. This needs just this does not need any other star, but it explodes due to its own collapse. Okay, so that is roughly the difference between these two. Now whatever be the origin or the nature of the supernova, it is true that in general whenever a supernova explodes, it generates a blast wave type of thing from the center of the explosion. Okay, you can simply think that a very small volume, okay, in space, it emits suddenly an enormous amount of energy like this. For example, the explosion of a bomb, okay, this type of thing. So, and it creates a blast wave. So the blast wave is nothing but a wave of enormous amplitude and cannot be added by superposition. So you cannot just add them linearly to get the resultant. So if you add two, if you want to have the effect of two blast waves, okay, the combined effect, the addition of the waves cannot give you simply the combined effect, okay, because this is non-linearity should be taken into account. Now, so these blast waves are caused by the supernova explosion, and in our discussion we will mainly be addressing the nature and the physics of that blast wave, okay. Now whenever a supernova explosion takes place, okay, from the images which are obtained generally by astronomical means, they are usually found to be nearly spherical, okay. So this is a typical image of the supernova SN1572 explosion. This image is taken from Arnav Rai Chaudhury's book, one of the reference books which I gave you for this course, okay. Now this SN1572 is a supernova which exploded in this manner, and you can see this is almost spherical, okay. Now it is true that this is, I mean, very common sense that if the center of the explosion is nearly point-like, and let's say it's not like a dumbbell shaped, or it's not like something like a conical shaped type of thing, but it's a point-like thing like this or spherical, then the initial explosion can be expected to be isotropic. That means there is no directional preference for that explosion, okay. So if we have an initial isotropic explosion plus if the ambience, so this is the, I mean, so after the explosion, the blast wave should be expanded in the ambient medium, okay. This is the surrounding medium. So if the ambient medium does not have any stark, I mean, non-uniformity, that means it is more or less homogeneous or uniform, okay, then the blast wave is actually expanded also in a spherically symmetric manner. That means there is nothing to damage the directional unbiasedness of the whole process, right? Of course, it is now easy to see that there will be prominent difference which is finite just inside and outside of the outermost surface of the blast wave. So if you just check of this, for example, so this is the blast wave front, right? And so let's say the fluid just outside this and just inside this is very much different, because the inside this contains the, I mean, the exploded material, right? It has a totally different density, energy, pressure, right, velocity, whereas the, I mean, the medium outside is simply undisturbed medium, undisturbed surrounding ambient medium, right? So it can then be this front, this blast wave front can then be considered like a shock front, correct? This one, okay. So this can be considered like a shock front, because here this is the medium which is totally influenced by the explosion, and this medium is till now undisturbed or uninterrupted by the disturbance, okay. Now you see that this shock wave then, I mean, so this shock wave is then assumed to, I mean, expand spherically outward in the outward direction, okay. But we will come to this point later, that how we will use the different properties of a shock wave, okay, as we did last time, okay. That means the famous Rankine-Hugoniot condition type of thing, and using that, how can we determine, or how can we infer on the structure of the structure of the blast wave front, and also the jumps of the density, velocity, this type of thing, that we will do later. But now we will do something very interesting and very simple. By using some simplistic approximations and very crude dimensional analysis, actually Zedov in the year 1946 and Taylor in the year 1950, both of them correctly predicted something very interesting. They predicted that the law of evolution of the blast wave front of an energetic explosion correctly, and that we will see. Okay, so they did not use any formal analysis for that. They just used very rough dimensional analysis, but they used another very simplistic approximation, which comes out to be very useful and very reasonable for this type of blast wave expansion. So that is this point, that both Zedov and Taylor, they showed that the above problem of expansion can be solved very easily by assuming the evolution to be self-similar. So they assumed that the expansion of the blast waves takes place in a self-similar way. Now, of course, the first question comes to our mind is, what a self-similar process means in this context. Okay, so self-similarity is something which is tremendously used in various domains of physics, starting from large astrophysical things, as you will see, to microscopic systems. Okay, so here we will try to understand what self-similarity is from a very from a very practical point of view. Okay, there are much more mathematically rigorous definition of self-similarity in several cases. Okay, but here we just say very simply that an evolution is self-similar if a subsequent configuration, that means a configuration at a later instant, can simply be obtained by multiplying each distance of the initial configuration by a constant factor. That means if the initial configuration is given by this and the later configuration is given by this, then if the distance between 2 points on this sphere is multiplied by 2, okay, when we trace those 2 points on this sphere, okay, then if we take any other points here and here and calculate the distance of these 2 points, between these 2 points on this sphere and this sphere, we will see that this distance is also multiplied by 2. If this is true, then we will say that the system is expanded or evolved in a self-similar manner. Another way of saying this is that the initial configuration, basically, so if the initial configuration, let's say like this, then if it is a self-similar expansion, then after that the configuration globally does not change. Okay, now of course, when I say that an evolution, when I say that a subsequent configuration, that is a subsequent configuration at a later instant, let's say t, okay, can be obtained by simply multiplying each distance of the initial configuration by a constant factor m. But this m is constant, okay, for any 2 points, okay, on the spheres, given we are now concentrating on a given value of t. Let's say after 5 seconds, okay, from the initial point or starting point, okay, 5 seconds after the explosion, for example, then this m has a constant value. Of course, if we now try to go to the another instant, that means we try to study how it looks like. Okay, at t is equal to 10, that means 10 seconds after the explosion instance, then there will be, every distance will be again multiplied by the same constant factor, but that will be some m prime. Okay, so for configurations at two different time instants, the constant factors will change. Okay, so for every time instant there is a specific constant factor. We will come into that in a much more schematic way, that will be much more clear at that point. Now you will see all these things specifically leads to the conclusion that the following configuration or the subsequent configuration is nothing but an enlargement of initial configuration, right? So fortunately we can see that this is a very useful assumption, but we don't know how reasonable or how relevant this assumption is for our case. But fortunately, self-similarity actually holds reasonably good during an important phase of supernova explosions and in other problems involving blast waves. Okay, one such problem is the explosion of an atom bomb. And for your kind information, for the first time when Taylor, for example, Taylor was working on this blast wave thing, he was actually working to analyze the effect of the explosion of an atom bomb. And that's why only after the, he was working during the Second World War, and only after the war ended, his research papers were declassified by the government, and it got published, and finally people knew about it. So now let us try to associate the present case, okay, now the present case with the general introduction of shocks. Okay, so for example, now we are talking about the something is expanding, this surface of discontinuity is expanding in a spherically symmetric way outward, in the outward direction, from the center to the outward direction. But previously when we talked about the surface of the shock, then we said that the shock is actually going like this way, okay, in a medium, undisturbed medium like this. So this is the front part of the medium and this is the back part of the medium, that we said, right? If you remember the picture. Okay, so here if we just think that we have a shock, but the shock itself has a spherical shape, the shock is now no longer like this upright front type of thing, but it's a spherical front. Then we can actually think that this shock, the part which is in front of the shock is this part, that is the surroundings or the ambience, and then its velocities are given by v1 rho 1 p1, and the velocities, the velocity, density and the pressure, they are given for the medium which are behind the shock, and which contains all the information about the explosion. They are designated by v2 rho 2 and p2. Okay, and here this is the center of explosion. Okay, now in our case we have we now assume that the whole thing is taking place in a self-similar way. So now coming to schematically the meaning of self-similar way. So what I just said that, so an explosion, let's say, is generated, okay, and due to the explosion nearly spherical blast wave is generated, and its expansion is nearly self-similar or self-similar. Okay, our assumption is self-similar. Then self-similarity simply says that if we just take the previous configuration and the subsequent configuration, okay, then if we just level two shells. Okay, one is an intermediate shell of radius r1, another is the, let's say for example any other radius. Let's take the front, okay, the outermost surface of the blast wave, which is rs, the radius. Okay, you can see here clearly. And now if we simply say that this one is for a later instant, this one is now going into this, and this one is going into this. Okay, then this now becomes rs prime, and this one becomes r1 prime. So the definition of the self similarity simply says that r1 prime by r1 will be equal to rs prime by rs, and it can be true for any other two radiuses, two radii actually, sorry, two radii in the final and the initial configuration. So it can be for any other, let's say r2 prime by r2 or any other rn prime by rn. And this constant factor is a constant for a time instant, for a given time instant. Let's say we are now checking what happens t seconds after the point of explosion, and we call that proportionality constant to be, or the ratio, constant ratio factor to be alpha t. Okay, so alpha t is constant for all type of ratios, but this changes when I change the t. Okay, so one thing is true, that every r1 prime you can write is equal to, so r1 prime will be alpha t r1, rs prime will be alpha t rs, and for any arbitrary rn prime will be alpha t rn. Okay, so at an arbitrary instant t for two distances ri prime and rj prime, so now let's say we are just concentrating on one sphere, okay, but everything in in a later instant. So but we are now concentrating, before we were concentrating on the green one in 2 configuration, the red one in 2 configuration. Now we are concentrating on the two different radii in the same configuration. Okay, and we will see that what it gives. So let's say two distances or two radii we have taken for the from the later configuration. Okay, so ri prime and rj prime. Okay, so ri prime by rj prime will simply then be equal to alpha t ri and alpha t rj, and you know, so alpha t will go out, then this ratio will simply be ri by rj. So another way of saying the self similarity is that so now the question is that, so you understand, so this ri by rj will be actually equal to ri prime by rj prime. So the ratio of two radii is constant, and it is constant over time. So this constant's value does not depend on the time instant chosen, but this constant value is depends on the choice of ing. Okay, so let's say if you now take, for example, red and green, you have one value of xi, and if you take red and this one intermediate one, you will have another value of xi. If you take green and this intermediate radius, you will have another value of xi. So xi's value is independent of j. Okay, because this gives us the fixed ratio of two given two two given shells over time. Okay, so this one, so this factor is independent of time. So we can say that a self-similar expansion is nothing but an expansion in which the ratio between two given shells, I mean in our context of course, okay, where we have a number of concentric shells, spherical shells, then the ratio of two given shells in the later configuration and in the primary configuration, they are independent of time. Okay. Now for convenience, the ratio of any radius r to that of the blast wave front, let's say lambda, is expressed just as xi r. Okay, so we are just removing two indices like this, and we just say that let's say this rj is nothing but the wavefront itself, that is the lambda, and r is any arbitrary radius. So then xi r will be nothing but rt by lambda t. Okay, so that is simply xi r, and of course you have to remember that for a given r and so if you just label your shells in one instant, so it will simply be equal to r prime t prime by, actually I should have written like this, is equal to r t prime lambda t prime. Okay, this is also equal to. Now the question is how to calculate lambda. If so, this is something fixed for a given r. If we know lambda, but we have to now know lambda. Okay. Now lambda denotes the size of the blast wave. Now, how to determine that? At this point, we need to use the very powerful but very simple dimensional analysis, and for that we have to understand first, or we have to determine on which factors lambda t depends. Now for a system, by very using usual common sense, one can simply say that lambda t is an explicit function of time. That is true, because this is an expansion, so there is an explicit function of time. Okay, if nothing changes but only time changes, lambda will change, because it's a size and it changes with time because it expands. Okay, the system, the front is in motion. Now there is another thing, the energy of the explosion. If let's say if the time is frozen, but we are just checking two explosions, one has an energy E1, another is E2, of course we can from our intuition we can say that the energy will mostly be converted in the kinetic energy of the blast wave envelope, and so if E1 is greater than E2, then the blast wave velocity, front velocity, will be greater than that of the blast wave front velocity for the E2. So the size will be greater for greater E1. Okay, and the ambient density. So now the whole thing should go. So if you now remember this picture, the whole thing should go or should expand in the ambience. If the ambient density is very low, then the system will have facility, or this will facilitate the expansion process of this shock front. If this is high, then the system has to fight against the density of the surrounding, right? And then the size is not that large. So we can think that this can actually play an inverse role with the size of the blast wave. Now how is that? We can do with a very simplistic way. And any other thing, there can be pressure of the surrounding, but for instance we just assume that the pressure of the surroundings, so we assume the pressure of ambience, says P1 is tends to 0. It's very, very low. So we are just taking all these three: energy, ambient density, and time. Okay. Now let us simply write that lambda, which is the size of the blast wave, okay, is equal to e to the power alpha, t to the power beta, rho 1 to the power gamma. Okay. We just assume that all these are the only three factors which can determine lambda. Okay. Now it is true that lambda has a dimension of length, so it will be m0 l1 t0. E has a dimension of energy, m1 l2 t minus 2. It's like mv squared. Okay. T will have the dimension of time purely, m0 l0 t1, and rho 1 is nothing but the mass density, which is m1 l minus 3 t0. So if we combine all these dimensions according to this rule, okay, finally we will have alpha plus gamma is equal to 0, 2 alpha minus 3 gamma is equal to 1, and minus 2 alpha plus beta is equal to 0. Now if we solve this above set of equations, we can see that alpha is equal to 1 by 5, beta is equal to 2 by 5, and gamma is equal to minus 1 by 5. So finally one can show that this simplistic estimate of lambda just by using a dimension analysis, which is not analytically rigorous, but simply it gives us a rough form of the dependence of lambda with as a function of time and with also energy and the density of the ambience. So it will be given by E t square by rho 1 whole to the power 1 by 5. So for a given explosion and given ambience, E and rho 1, they are fixed. So lambda t will simply be proportional to t to the power 2 by 5. So that is the conclusion. If that works well, then we will think that our whole theory and this construction of the self-similarity, this works well. Now, of course, that was all about lambda, but to understand what about, but to determine any arbitrary radius at some given instant, at some instant t, then this will be simply be equal to xi r lambda t, and that is equal to xi r times e t square by rho 1 to the power 1 by 5. So in order to have information about RT, in addition to lambda t, we have to have no xi r as well. Okay. So that information is needed. Now, now coming back to the size of the blast wave, then we have to concentrate on the blast front, and this RT is nothing but lambda t itself. So at blast front, the RT is lambda t, right? So xi lambda is equal to 1, and we know what it is. So lambda t, then lambda t or RT, whatever, there's the same thing, then they're approximately equal to this one, that is equal to simply E t square by rho 1 whole to the power 1 by 5. So lambda t is proportional to t to the power 2 by 5, and v lambda t, with which the velocity with which the blast wave front expands in the surroundings is given by d lambda dt, and which is 2 by 5 e by rho 1 whole to the power 1 by 5 times t to the power minus 3 by 5. Hey, look, can you feel something strange? Well, that means that although lambda changes or lambda actually increases with time, v lambda actually decreases with time. And here you see that that is a very stark difference with the velocity of the shock front decreases with time, and this is a very stark difference with the stellar wind expansion, where, for example, when we were talking about the solar wind, we saw that this is basically the, becoming from subsonic to supersonic, and that's the observed fact. But here, this is the opposite thing which is happening. The velocity is actually reducing. Okay. Now the question is that it is true that whenever we are talking about this type of blast wave expansion or something, so we are thinking that the shock wave is expanding, and the shock waves are not exactly the same as the solar wind plasma expansion. But it is true that once the solar wind becomes supersonic, can somehow this type of shock wave formation is possible there. So is it like that, that maybe after gaining the supersonic speed, maybe there is a reduction of the stellar wind velocity with time? You have to search. This is the research part. Okay, so there is also something which is expanding, and we don't know whether the speed is actually, so we know that there is an acceleration from its origin near sun for the stellar wind, and from its subsonic regime to supersonic regime. But what really happens after attaining the supersonic regime, that we have to think, and only then we can think the analogy, or we can somehow try to compare them with this type of shock front. Of course, this shock front is a very, very strong shock. Okay, so just check and see that which type of researches are being done on that. So what I can tell you, that this is a very active domain of research. Okay, so coming back to this one, that we predicted, Zedov and Taylor, they predicted a t to the power 2 by 5 variation of the size of the blast wave explosion, okay, as a function of time. And that was actually precisely verified from the test movie of the atomic explosion, so by Taylor. So Taylor just took them, estimated the sizes of the blast wave from the different instants taken from a movie of the atomic bomb explosion in 1945 at New Mexico. Okay, so just by observing the movie at the explosion, Taylor obtained the plot which showed a fantastic agreement with the lambda t proportional to t to the power 2 by 5, and the plot was like that. So it was a log-log plot, if you see. So of course the plots are not log-log, but the quantities which are plotted, they are logarithmic quantities. So log r versus log t, actually 5 by 2 times log r by log t, and you can see that finally there is a fantastic straight line with slope 45 degrees. So finally you can see that this one is holding excellent. Okay, now what's the conclusion? The conclusion is that our basic hypothesis, or the basic assumption, that the expansion of blast wave is self-similar is actually true. Now let us just take a typical supernova explosion for the order of magnitude. Okay, and for such explosion, actually the mass ejected is of the order of 1 solar mass. Okay, and the initial velocity is 10 to the power 4 kilometer per second. That means the velocity with which the system the blast wave starts expanding just after the explosion, it gives us an initial kinetic energy of 10 to the power 51 arc. Okay, now just by taking a typical very, very dilute interstellar medium type of thing, you can see that the density is 2 into 10 to the power minus 24 gram per cubic centimeter. Okay, and if you use that, you can actually see that some straightforward calculation gives us lambda t is almost equal to 0.3 times t to the power 2 by 5, where the lambda is in parsec. Okay, and v lambda t is almost equal to 10 to the power 5 times t to the power 3 by 5 in kilometers per second, and in both the cases the time is in years. Okay, that's much more practical. Okay, now what is the strange point? The strange point is that if you see that, if you notice carefully, that v lambda is equal to 10 to the power 4 kilometer per second when t is almost equal to 100 years. But we know from our knowledge that we supplied v lambda is equal to 10 to the power 4 kilometer per second at the time of the explosion. That means it was the initial velocity. So why is this discrepancy? That is simply because the method by which we determined this formulae was not rigorous. It was very, hand-waving dimensional analysis. And this dimensional analysis cannot give you, for example, if let's say that, for example, if in reality there is some dimensionless number n, for example, then dimensional analysis cannot give you any news of that. That is something, a drawback. Another drawback which we will understand here now. So we can see that the initial velocity actually is calculated finally from the final form as a velocity after t is equal to 100 years. So how to solve that? That is simply to say that, okay, so this is not the correct formula. The correct form is like this. V lambda t is almost equal to 10 to the power 5 times t plus 100 10 to the minus whole to the power minus 3 by 5. So it simply says that there is a shift in origin, okay, in the original formula. So let's say if someone now today derives this type of formula from analytical considerations, he or she should get this form. Okay, and that actually says you that when t is equal to when t is equal to 0, okay, when t is equal to 0, then this part is actually 100, and so we have v lambda is equal to 10 to the power 4 kilometers per second, and we agree with that. So that was the solution of this discrepancy. Now the final thing is that in this whole discussion we just used some very simplistic approximations and assumptions and dimensional analysis method to understand how the blast wave evolves with time. Okay, so it is true that here we did not do any formal analysis of the shock and the, okay, so that we will do in the next lecture, but here we just showed that by simple things you can do very interesting thing in astrophysical premise. And the last thing is that, so all this analysis holds very good within 10 to the power 5 years after explosion, beyond which it is usually found that the energy is lost sufficiently due to radiative cooling, and then this type of law will not hold any longer because E will be no longer a constant. Okay, so there will be radiative cooling from the blast wave, so then you have to calculate accordingly. Okay, so that was all about the introductory part of the blast wave. Okay, and also we showed that how simplistic things give us an idea of the blast waves development with time, and how actually we could cross-check the very hypothesis of self-similarity both for supernova explosion and also a very important terrestrial application, that is the application of the explosion of the atom bombs. Okay, so this is also very much interesting things that we have to think that which type of correspondences we can draw every day with astrophysics to our everyday life. There are not so many, but if we can somehow bring, I mean, some of the correspondence, I mean, why not? I mean, this is always very much recommended. Okay, so in the next lecture we will use the basic conditions, Rankine-Hugoniot conditions of shocks, and we will do something much more analytical, okay, to see the structure and the jumps over the blast waves. Okay, thank you very much.